Hi everyone, my name is Preksha from the Department of Information Science and Engineering from Sri Venkateswara College of Engineering. This is my technical seminar presentation on the topic CloudNet, a LiDAR-based phase anti-spoofing model that is robust against light variation. I am presenting this under the guidance of Dr. Shalini V from the Department of ISC. These are the contents of my paper. Let's start with the introduction. Face recognition systems are widely used but vulnerable to presentation attacks such as print, replay, and 3D masks. Over time, industries have tried to secure a model with lower errors, even if the costs are higher, and multiple studies have been conducted for this. The study I am referring to was conducted just last year in South Korea. A LiDAR-based multimodal FAS models use 3D spatial and depth information as well as RGB color information, and they provide excellent performance mostly because they are also robust against light variations. So in this study, the CloudNet, a LiDAR-based FAS model, is proposed, which determines the liveliness of space using RGB images, point clouds, and depth images obtained from a LiDAR-based FAS model, which is superior because it is confirmed using three different protocols that demonstrate that the CloudNet sensors are more generalized than the RGB model. Next, we move on to the related background. I will be referring to three different studies that have been conducted and how the study that has been conducted on the paper I'm referring to improves on each of these studies. So the first one is the multimodal phase anti-spoofing. So this study is based on deep learning phase-based anti-spoofing, is divided into two categories based on the sensor that is used. So one is the commercial RGB cameras, and they're specialized in sensors such as NIR, SWIR, depth, thermal, light field, and four-way polarization cameras. This study uses a LiDAR sensor, which is a time-of-flight-based depth sensor. The other sensor it uses also specializes in improved FAS accuracy in high security scenarios that require a low rate of false acceptance. The second study is the multimodal fusion, which is a technique that combines data from different sources to achieve better results. It has been applied in fields such as effective computing and autonomous driving. This technique uses three methods to combine data. That is the early fusion, the middle fusion, and the late fusion. So the early fusion combines data at the pre-processing stage. The middle fusion combines data during the feature extraction phase, and the late fusion combines the output from the multiple models to produce the final result. The third study is the LiDAR sensor and point cloud. The LiDAR sensor uses a light signal to calculate distance and generates point cloud data, a 3D representation of the target. The point cloud can be learned in deep learning models using three approaches: projection onto a 2D plane with 2D CNNs, voxel-based learning with 3D CNNs, or pixel-by-pixel learning. So the recent methods like SqueezeZVT and FBSNet address feature distribution changes in LiDAR images, improving deep learning from point cloud data that helps with better sensing of the facial features. Now we move on to the working of the model that is built. So the LiDAR dataset for phase anti-spoofing, in short LDFAS, the dataset that is used for this study composes of 8,640 phase data collected from 36 trillions. So the images are considered in three different scenarios. to be able to study for RGB, point cloud, and depth configurations. So the LiDAR application is an ArtKit-based mobile app that simultaneously generates RGB, point cloud, and depth data that was used. This camera also provides information on how to map all points in the point cloud to a specific pixel of the RGB image. Depth images are derived from the point clouds. So the data collection procedure is in which all participants were instructed to sit in front of the camera and look towards the seating. And so in the data collection procedure, the participants were instructed to sit directly in front of the camera and look towards the sensor. And three subsets of data is collected: indoor, outdoor, and indoor, but with better light. So the images turn out to be much darker than the indoor versions. This is the image provided for the LiDAR dataset for face anti-spoofing of three different Koreans in three different sets. That is the indoor, outdoor, and the indoor dark. You can also see the RGB images, the depth images, and the point cloud images that is derived from the other two. In this slide, you can refer to the tables 2 and 3 for an explanation on the subsets of the LiDAR datasets face anti-spoofing. You notice that all three subsets, that is the indoor, the outdoor, and the indoor dark, vary in background, with only indoor having a constant background, whereas the other two have variable backgrounds, but the components remain the same, which is the RGB, point cloud, and depth. So we consider 12 subjects for each of these subsets, and the training number of training data and number of test data is also given in table 4, which training data is 720 for each of the subsets, whereas the test data is 240 for the indoor subset, whereas 960 for the other two. So the evaluation protocols, three of them were designed. Protocol 1 corresponds to when the learning and the test data sets are in the same light conditions. So by contrast, protocols 2 and 3 used different light conditions. So the proposed method, um, the CloudNet architecture is explained. The structure is composed of a red, green, blue space and LiDAR space networks. Each network extracts spatial features from the RGB and LiDAR data, which is the point cloud and depth. The CloudNet performs both early fusion and late fusion to classify the bona fide and spoofing images. This is the architecture of CloudNet. As you can see, it has an early fusion and late fusion process. In the early fusion, the point cloud and the depth data is combined, whereas the product of this is combined with the RGB in the late fusion process. Together, it gives a different result. The RGB, LiDAR, and CloudNet models were tested according to three different protocols, which is the BPCR, that is the Bonafide Presentation Classification Error Rate, the APCR, which is the Adapt Presentation Classification Error Rate, and the ACER, which is the Average Classification Error Rate, which were used as the evaluation metrics. And the table 5 describes these under protocol 1. The BPCR, APCR, and the ACER are studied under protocols 2 and 3, as the table 6 and 7 describe. The error rates is different in each of these studies. The image that is displayed is the study of the RGB model, LiDAR model, and CloudNet model under the three different protocols. As you can clearly notice, the difference in the point cloud data, it proves that the CloudNet data had the least change in error, thus proving that the CloudNet model is better than the RGB and the LiDAR models. As for the future enhancement, the study found that the performance of the RGB model decreased significantly when tested on datasets with domain shift in light. Thus, using LiDAR sensors were found to improve this because they're robust against light changes. So the CloudNet can be further improved in performance compared to the LiDAR model, but with a higher computational cost. The future studies may focus on reducing this cost of the CloudNet model while maintaining its performance. In conclusion, the study proposed a 3D facial recognition FAS model using LiDAR and RGB camera with LiDAR's 3D coordinate and depth information, which provides the robustness against light radiation. The LDFAS with different light subsets were confirmed to have more error rates than the CloudNet, but the CloudNet's weight was heavier than a regular LiDAR model. Therefore, the study shows that the LiDAR sensors can be a valuable addition because it provides robustness to light radiation. But the model lightweighting can also be a crucial factor in improving the efficiency and effectiveness of these models. Now, coming to the references, I have reference to several papers that are already referenced to in this study. Some of them include the eye blink detection based on multiple reported response rates. The second one is assuring liveness and biometric identity authentication by real-time face tracking. The third one is the learning deep models for face anti-spoofing, binary or auxiliary supervision. Fourth is the learning deep models for face anti-spoofing, binary or auxiliary supervision. The rest of them include using LiDAR and images for pedestrian detection using convolutional neural networks, automotive LiDAR technology, which is a survey, the squeeze phase, the automatic measurements of garment sizes using computer vision deep learning models and point cloud data, generating 3D adversarial point clouds under the principle of LiDARs. And that is it for this presentation. Thank you so much for watching it. Make sure you like the video because that would help me out a lot. Thanks.